Hello everyone and welcome to video number 10 of this series in which we are learning how to model an end plate steel connection, which is this model that you see here. In the previous video, we have finished defining the mathematical model of the type boundary value problem here in ANSA, which is the preprocessor software that we are using. And then we have outputted the .inp file by clicking on File, Output, Abaqus. And in the working folder, this file has been generated, the .inp file. And then we used this file. Let's remember that we have opened a CMD. And then we have submitted this job like Abaqus J equals and the name of the file without extension. And then we can also use a command here to establish how many CPUs we want to use, such as 18, for example. When we press enter here, we end up submitting this job to Abaqus, and then Abaqus is going to solve this mathematical model using the finite element method. And we know that this solution is approximated. After doing that, Abaqus has generated all these files that you see here. In this video, we are going to post-process the results by using the .odb file. But before we do that, let's analyze some of these files that were generated. We are going to specifically analyze the .msg file and the .sta file. These are two important files that we should analyze. Okay. So let's start then. Actually, we're going to also analyze the .inp file. Let's start with this one, the .inp file. I suggest you to install Notepad++ to analyze these files. And then after installing it, right-click on the .inp file and then click on Edit with Notepad++. And here we have the definition of this mathematical model that has been solved. We are used to this file. We have stated this file many times before in other exercises. So first of all, we have the definition of the nodes. And then if I Control F and search for element with this symbol, I'm not sure how to say that. I mean, I guess this is asterisk, right? Asterisk. If I search for asterisk element, here we have the definition of the element. We have as4 shell element being used. And this is a good type of element for this analysis because you're going to see that we're going to have large strings occurring. And this element allows finite string. And remember that finite string means large strings. Okay, it uses a finite string tensor in its formulation instead of an infinitesimal string tensor. Anyways, this is something related to theory that we have learned in details in previously in this course. Let's go. Well, I'm not going to see everything in this file. Let's just study what is more important. Let's see the definition of material. So search for asterisk material. Press enter, close, and then in here we have the definition of all materials that we have here in the material list. We have 3 materials, right? So let's see how this is defined here. So first of all, we have this command to define a new material, and then we can give it a name equals, and then here we have the name. We also have this M1, which is just the MID in ANSA. So ANSA puts the MID of the material here. You see, this material is the one with ID 1. So that's why we have material 1 here. Here we have the definition of density in tons per cubic millimeter. And then here we have the definition of the elastic properties. So the material is isotropic. It behaves in the same manner in all directions. Modulus of elasticity is equal to this value, Poisson's ratio. And here we have the plastic properties of this material. We have isotropic hardening because we have monotonic loading here, so isotropic hardening is good enough. And then we have yield strength for zero plastic strain, and the same value of stress for 0.1 plastic strain. This means that we have a perfectly plastic material model here. So we don't have strain hardening occurring. This is a conservative material modeling approach. And then in here we have the definition of the next material, density, elastic properties, plastic properties. So you see that the yield strength of this one is lesser. And then we have the definition of the bolt material here, density, elastic property. And then in the plastic property, we have more points. This is the trilinear material approach that we have used here. Okay, so this is pretty easy, and this is also very easy to modify if we need to. Again, remember that when I need to modify just simple things, I usually modify in the .inp file. And if you get to work in the industry, you're gonna see that this is something that is done a lot. Okay, so simple modifications are done here in the .inp file instead of modifying in here and then going again in file, output, Abaqus, and etc. Here we have the definition of contact. We have only one contact defined. So in the definition of a contact, we have this command, comma, and then the second argument is the interaction that has been used, which is this one with this name. This is defined in another part of this document. We're going to search for this interaction definition shortly. And then the next argument is the type of contact, in this case, surface to surface. And then a small sliding formulation. We have used a small sliding formulation. We can go back here to contact, double click on this, and then you see that we have used a small sliding formulation. This is a kind of formulation that is less, the computational cost is smaller, and we can use it only when we have a small sliding, which is the case here. Okay. And then in here we have the slave surface that was used in this contact definition and the master surface. So first of all, let's see the definition of this interaction. So select this, and after that, Control F, and then click on Find Next. And then in here we have the definition of this interaction. So you see that this definition is done by this command, surface interaction, and then we have the name, and then this is just a comment. Every time we have two asterisks, this means a comment, and this is an internal comment made by ANSA, so we can ignore it. This is just to tell the ID. Well, this is the information of the ID in ANSA for this interaction. And then we have this command here. So we have a friction defined in this surface interaction, and that's all we have defined here. And then the friction is equal to 0.44. Okay, in this case, we have only this defined in this interaction. Now let me go back to contact. So search for asterisk contact. And then in here, let's search for the definition of the surface that has been used here. Control F, and then find next. And then in here we have this surface defined. So this surface is defined by using this command. And then we have the name of this surface, and then the type, element. And then we have a comment here we can ignore. And then in here we have the element set that has been used to define this surface of the type element. Now we can search for this element set. So select and Control F. find next. And then in here we have the definition of this element set. This is the command to define it. And then here we have the name. And here we have the ID of the elements that are part of this element set. So you see, it's easy to analyze this document. And it's very important to develop this skill. So we have understood how the contact is defined and the surface of the contact and also the interaction. Let's go to the next important thing here, which is the step. So search for asterisk step. And then in here we have the definition of the first step. This is just comments. Here we have the definition itself, name. And this is very important. The geometric nonlinearity algorithm is activated, and a symmetric matrix storage is activated as well. Here we have just a description of this step. The kind is static, so we're going to have the equilibrium equations as the governing equations, those three partial differential equations. We're going to start with an increment of 10% out of 1, minimum 1e minus 9, and maximum 0.2. Here we have the definition of the gravity in the minus z direction. Here we have the definition of the connector load. So this is the command, the set of connectors that is defined. So let me Control F this. And then you see that we have this set defined here. Well, actually, this is the definition of the connector element itself. And in this definition, we have automatically created this element set that was used there. Let me press enter to go back. Here we have the element set definition containing the connector element. And here we are again back to connector load. So we are applying this connector load in this set in the first degree of freedom, that is x one direction. And this is the value of the connector load. Because of the way that we have defined it, we needed to assign a negative value. And then in here we have the definition of the output requests. So first of all, a field output request, and then we have all these as field output request. So everything that is below the field output request is a field output request. So we have a node output, reaction force and displacement, element output, equivalent plastic strain and stress components and invariants, contact output, we have these three. And then here we have the history output request for every increment. And then below that, we have this node output request for the measured rotation node, which is a node here in this region. And then we are asking rotations, and then node output request for the displacement node, which is this node that we have the displacement applied, and I want to calculate reaction force and displacement, and then end of step. For step 2, we have the definition of this step, name, geometric nonlinearity activated, and symmetric matrix storage, a comment, governing equations, initial increment out of this total, minimum, maximum. And then you see we have this important command here. This is something new. This command, connector load, comma, OP equals new, this means that we are resetting the connector load boundary conditions. So every connector load that has been defined previously, in this case, in the first step, we had this defined here, is going to be eliminated. It's not going to be propagated to step 2, because the idea here is to substitute this connector load by this connector motion that we have here. So connector motion fixed of the set of translators, connector translators, we're going to fix the first degree of freedom, which means that the relative position between the two nodes of the translator connector is going to be kept as constant. Remember that when we apply the connector load, the software moves this node until it reaches the connector load. And then in here, we're going to fix this position as constant. Okay, here we have the definition of the boundary condition of the type displacement in this node, z direction minus 200 millimeters, ends, end of step. And then in here, we just have comments. So now we are finished studying this document. You saw that I was pretty fast here because this is something that you already know how to analyze. Okay, so this was just one additional exercise. Let me close this. Let me close. Now let's go to the next study. Let me see how much time I have spent. 16 minutes. Let's analyze the .sta file now. So right click and edit with Notepad++. And then, well, this file is really, really important. Here we have the information about increments and iterations of equilibrium. Let me open board. And I guess I have opened here one file that I need to show to you. This is something that we have stated in details. Let me see. We have this file open with some annotations. Let me get one image here that is important. Yeah, maybe this one here. Yeah. Guys, remember that in a non-linear finite element analysis, the stiffness varies while we apply the loads, the external loads. In this case, we have a displacement applied here, and the connector loads, and also the body force, which is gravity. So these are the loads. Even this displacement is a load because we know that this is going to yield to a reaction force. So we can think about it as an external load that is being applied. So while we have, for example, this displacement occurring, the stiffness of this whole structure is going to change because this is a nonlinear analysis, because we have material nonlinearity due to plasticity, we have large displacements and large deformations, nonlinearity, and we also have contact nonlinearity. We have a contact here with friction that allows sliding and also separation. And because of, well, and then because the stiffness varies, we need to solve this problem by increments of loads. So instead of applying here 200 millimeters of displacement, we are going to start applying 1 millimeter of displacement, which is the first increment that we have, which is this first line here, right? So you see, in this column, we have the increment that was applied. So we have 10%, 0.1. This is 10% because the total is 1, because we have defined it as like this. And we know that this means 1 millimeter because, sorry, we don't have the displacement applied in this first step. We have the connector loads applied here. So 10% of this connector load that we have applied. Okay, so in the first increments, we're going to have then 15.5 kilonewtons of connector load being applied. And then this is the total time increment, 10%. Here we have also this step time increment. You're going to understand it. You're going to understand these two columns in the next rows. So in this first increment, you see that we had a total of 23 equilibrium iterations. So it was not easy to converge this first increment, and this is something that is common. Usually in the first increment, we have some difficulties to converge. And then you see that this is total iterations, right? In this column, we have severe discontinuity iterations. So we had 21, and in here we have equilibrium iterations. Let's understand what is severe discontinuities. To understand that, we should go to Abaqus manual. In your case, if you don't want to access it through the PDFs, you can just search on the internet. You're going to easily find what I'm going to show here. It is in the second volume. And then in here, it is in the analysis procedures and analysis solution control, solving nonlinear problems. No, analysis convergence controls. And then convergence criteria for nonlinear problems. If you search for these on the internet, you're going to find this material that I'm going to show here. Let's scroll down to see where we find this information. It is here, severe discontinuity iterations. Abaqus standard distinguishes between regular equilibrium iterations, in which the solution varies smoothly, and severe discontinuity iterations, in which abrupt changes in stiffness occur. So that's the difference. Severe discontinuity iterations occurs when we have severe discontinuities, which means that we are going to have a large variation of stiffness in these iterations of equilibrium. So you can think about it as a different kind of solver that is applicable for when we have abrupt changes in stiffness. And then you see that we have these iterations of equilibrium, 21, and then after going through all these, the residuals, that is the force residuals and moment residuals, are going to be small enough for the software to perform a normal equilibrium iteration, which is named here as regular equilibrium iteration, in which the solution varies smoothly. Okay, so that's what we need to know. Obviously, that you can read here to know more about it, but we can only use this intuitive idea to understand it. Okay, so after performing all these equilibrium, and by the way, I have opened this to show to you what happens inside one increment. Let's just remember that when we have stated about the Newton-Raphson method, which is the method that is used here, we start with the first iteration of equilibrium with an initial guess of stiffness, which is this red line here, which with this inclination. And then a displacement is going to be calculated. And then with this, we're going to have the update of the stiffness matrix. And then with this, we're going to end up calculating an error here. And then this error is larger than the tolerance, because it's very large. And then I'll also remember that in here we have the representation of what is happening in one node of the structure and in one specific degree of freedom. Guys, for you that is watching this from YouTube, if you obviously didn't study about this in my previous classes that are not available on YouTube, so maybe you're not understanding this part. But for my students that have studied this, then this is something that they know. And then we have this large residual, which means that we should continue performing iterations of equilibrium. And then we go to the next one. And then in the next one, we have this new stiffness, we calculate this new displacement, and then we are going to have this error, and then we go to the next one and next one, until we find a displacement that is very near to the actual displacement of the analytical solution. If we had the analytical solution, right? So these are the iterations of equilibrium that occur inside this increment of load. It's just well, this is just a review of what we have studied. Okay, so in this case we have 23 iterations of equilibrium. And then for the next increment, the software has increased, actually has decreased to 7.5%, because it noticed it was quite hard to converge in the first increment, and then it automatically decreased the second increment to 7.5%. And then the total is now 17.5%. And then in here we have the same information. You're going to understand the difference between this column and this column shortly when we start the second step. And then in here we had only 2 equilibrium iterations. So we had no severe discontinuity iterations. We had only equilibrium iterations. So the variation in stiffness was not so abrupt. And then it converged, and then we go to the next increment, 7.5%, in total 25%, 2 equilibrium iterations, and so on until here. You see that it increased the increment here to 11.25%, and then 16.88, and then 20%. And it didn't increase more than that because we have established a limit of 20%. So in the next one, the increment was 20. And then in here, we had this final increment so that we have 100% in total. So you see that just the first increment was challenging and the next ones were all easy. And then we have the start of the second step. In the second step, we start with an increment of 0.005, which is 0.5%, which means 1 millimeter of displacement out of 200. And then we had 13 severe discontinuity iterations, and after that, 1 equilibrium iterations. You're going to see in the MSG file that firstly we have these iterations, and then we have this one. And then it converges with 14 in total, and then it goes to the next increment. Additional at 0.5%. Now we have in total 1%. Here we have 5 severe and 1, how it's saying, what is the word here? Irregular. 1 regular. And then it converges. In the next one, it increases the increment. And then you see that now you're going to understand the difference between this column and this column. In this column, it shows the total. Let's see firstly this column. In this column, you see that it shows the total load that has been applied. So since we are in the second step, here we have 1.02. Okay, so we had the first step completed and 2% of the second step, or almost 2%. And then in here it shows the total increment, not increment, but the total load that has been applied in the second step. Okay, so that's the difference. Well, anyways, we have here this increment, severe and regular, and then you see that in this increment we have something interesting occurring. Well, I have explained in the previous video of what this means, right? The software tried to apply this increment of load, and then it performed 4 severe discontinuity equilibrium iterations and 1 regular equilibrium iteration, and it noticed that the residual forces and moments, for example, were not decreasing. Maybe they were increasing. And then it decided that maybe trying this increment is not a good idea, so it's going to perform a cutback. So every time we have this U here, this means cutback. So this is the first cutback. You see that this column here is named as attempt. So here we have the first attempt for this increment. And then it's going to cut back, which means that in the second attempt, it's going to try a smaller increment. You see, this value is smaller than this value. And then in this second attempt, it performed 6 severe discontinuity equilibrium iterations and 1 regular, and in total 7, and it has converged. You see, we don't have the U here, so it means it has converged. And then in the next one, we converge, and then you see we have a cutback here again. Let's see this case here. For example, we have 2 cutbacks in a row. So in the first one, it tried to apply this increment, and then we had a cutback in the first attempt, and then it has decreased the increment, and then again it has we have a cutback in the second attempt, so 2U. And then in the third attempt, we have this smaller increment, and it has converged. Okay. And then the analysis goes like that until the end. I'm actually surprised that this converged until the end, because we have applied a pretty large displacement. Okay, guys. So now we finished analyzing these. Let's see. 31 minutes. Now let's go to the .msg file. Double click, right click and edit with Notepad++ this file. And then in here, well, this is one of the most important files to debug, because in here we are going to have information about residual forces and moments, and well, many other important information, as you're going to see. This file, is not so friendly, too easy to read. It's not that it's not friendly. It's just that to extract information out of it is not so practical. And that's why I usually use an application such as that one that I have suggested you to use in the previous video. The name of the application is msgfile.info. It's a website. So you can get, for example, this file, and there is this website, msgfile.info. I'm not going to use it here because I want to practice reading this raw file. It's a good idea to firstly learn how to read from here, and then to start using an application such as this website here. Okay. All right, guys, there is a lot of information here. I'm going to select just a few parts of this document to show to you. Because then I will spend less time. I'm going to show what really matters. So in here we have the definition of the criterion for residual force. Remember that we have learned about, let me see here. Yeah, the norm. We have learned about the norm, right? The norm is like epsilon here, which is the criterion of error that we can have. Well, this is a limit of error, and if we are below this limit, then we can consider the iteration of equilibrium converged, or the increment converged. So here we have the criterion for residual force. If the residual force norm is less than 5e minus 3, then we have the model converged. We have a criterion for displacement correction, which is 1e minus 2. A displacement correction is this correction that we have here. You see, from the previous attempt to the current attempt, we have this displacement correction. Let me see what is important here, and also you see we have criterion for residual moment and for rotation correction. We also have some other information here, but we're going to... this information is also very important. We are not going to deal with anything related to this in this specific example. Maybe in some future examples we can explore more what we have here, because these parameters that we have defined as standard values in Abaqus can be modified if we need to modify it. But in this case, we don't need to modify anything. So you see that in here we have the maximum number of increments that we can have, which is 100. This is something that we can modify if we'd like to. Large displacement theory will be used because we had NLG equals yes. Unsymmetric matrix storage and solution will be used because we have activated. Linear extrapolation will be used, and here we have the element length, 5 millimeters. This is not really important for static analysis. Let me see the next important information. Now increment 1 starts, and then we have attempt number 1. Time increment 0.10. So the initial increment is 10%. So in here we are talking about this increment. Well, I have used 18 CPUs to solve this analysis, so the solver is going to divide the elements between 18 CPUs. So in my case, I have like 8,000 elements per CPU. This is going to be different. I don't know how many CPUs you have used. But anyways, this information is not really so important. Let's go to what matters here. So you see that we have this information. 3,852 severe discontinuities occurred during this iteration. So because of that, this software is going to use a severe discontinuity iteration. It's going to apply this kind of iteration because we're going to have abrupt changes in the stiffness. So here we have the first equilibrium iteration of this kind. And then in here we have some information about contact. He shows the maximum penetration that we have, which is pretty small. He shows the node that we have this maximum penetration occurring. We also have this maximum contact force information and the node that we have this occurring. And then what matters is this message. The estimated contact force error is outside of convergence tolerances. So it didn't converge. So this is what matters. And then in here we have something related to force. And in Abaqus, this is named as flux. Flux can mean force or moment. So here we have the average force, and here we have the largest residual force, which is pretty large. Guys, the software is showing the largest residual force for a specific node in the mesh, in this case at this node, and it shows the degree of freedom. Okay, so it's like it's getting from a plot like this the error that we have for that specific iteration. Okay, this error that we have for that specific node and for that specific degree of freedom. Okay, so we are having this error, which is a pretty large value. Here we have the largest increment of displacement, which is equal to this value here, and it shows the node, and the largest correction to displacement, which is equal to this at these nodes and in this degree of freedom. And then what matters is that we have this information here that force equilibrium not achieved within tolerance. So it didn't converge. Here we have the same kind of information, but for moment. So here we have the largest residual moment, largest increments of rotation, and largest correction to rotation. And moment equilibrium not achieved within tolerance. So contact didn't converge, force equilibrium and moment equilibrium has not achieved convergence. So we need one additional equilibrium iteration. If we scroll down, you see that here we have the start of the second equilibrium iteration, which is a severe discontinuity iteration. And we're going to have the same kind of information. Contact, you see here, outside of convergence tolerances, not achieved convergence. And here we have a different message, rotation correction too large compared to rotation increment. So if the rotation correction, which is this parameter here, is too large if compared with this one, then we have this message, which is not good. And then it didn't converge, and then we go to the next iteration, to the third one, and then we're going to have the same kind of information. And then you see that we're going to have 21 like this. So I'm going to scroll down. Here we have the fourth, fifth. Let's continue. 9, 10. Let me be faster. 17, 20, 21, and it is 21. Yeah, 21. So in this last one, you see that now we have 3 severe discontinuities occurring. Remember that previously we had like 3,000. Now we have only 3. So the software is going to perform this last severe discontinuity iteration. You see that contact has not converged here. Force and moment has not have not converged as well. But we have just a few severe discontinuities. And for that reason, in the next equilibrium iteration, we are going to have a regular equilibrium iteration. So you see, equilibrium iteration 1. So now we are having the first equilibrium iteration here out of 2. And then in this one, the contact constraints have converged, but force did not converge and moment did not converge. And then we needed the second equilibrium iteration. Contact converged, force converged, and moment converged. Now everything has converged. The residual force and residual moment is pretty low, and then you see that we have this message here because of inconsistent convergence. Well, it's saying that it was not easy to converge this first increment. The next time increment will be reduced to 7.5%. Here we have that we had 23 total iterations, 21 severe and 2 regular, and we have this information, which is the same information that we have in these columns, and then we have the start of the second increment, 7.5%, and then here we have the first one, which is an equilibrium iteration. So we have, in this case, 2 equilibrium iterations. Contact converged, but force and moment equilibrium accepted based on small residual and estimated correction. So the moment has converged based on this assumption here, but force did not converge. So we need one additional equilibrium iteration, and then everything converges. Okay. Well, so that's the basics about the MSG file. It is this file that we use when we face convergence issues, because you can imagine that if we are having any convergence issues, then we can analyze here what is the node that we have the largest residual force or the largest residual moment, or the node that we have the largest penetration in the contact, or the node that we have the largest contact force. And then we can search for these nodes in the model, and anyways, we can start analyzing the reason why it's not converging. Maybe we are going to practice a little of it when we get to model these using solid elements for the bolts, washer, and nut. In this case, it was we didn't have any convergence issues. Actually, we had an overconstraint issue before, but we have fixed it. Okay, guys, so practice reading this document, go by line by line. In the beginning of this document, I didn't show everything to you. I really suggest you to go to read most of this information and to search in Abaqus users guides about some of this information. Over time, you're going to, it's not really a good idea to search in Abaqus manual about every information that you have here, because over time, you're going to slowly learn about it. You're going to face issues, and then based on these issues, you're going to need to research about some things related to this issue, and then slowly you're going to learn. That's the idea. Okay. All right. I guess I'm going to also show something related to a cutback. Yeah, maybe it's a good idea to to show what happens when we have a cutback. It was in the 7th. Let me search for this number here in this document, because maybe it's the best way we can search for that specific equilibrium iteration. Maybe let me search for this number. Backward direction. Nope. Well, I'm not sure how I'm going to find these. Let me search for these numbers here. Let me see how it displays here. I'm not really sure how to find that increment that has a cutback for me to show to you. Actually, let me go to the beginning of this increment, and then in here, let's see the text that we have in here, time increment 0.1. So that's the number. We have 3 decimal places. So we need to use here 3 decimal places, maybe like this. Yeah, I'm not really sure how to find it. So let me search for time increment, and let's go like this. Increment number 2. Oh, okay, this works. So increment number 5. In the first step, how many increments we have here? 1, 2, 3, 5, 6, 7, 8, 9. We have 9. So let's go through it. 8, 9. And then we have step 2 starting here. Okay, so step 2 starts here. And then we have so you see, it's not so easy to find information in this document. Here we have a time increment. So this is increment 1, right? Let's count here increment 1, 2, 3, 4, 5, 6, 7. In the 7th one, so increment 1, increment 2, 3, 4, 5, 6, 7. So here we have increment 7. Attempt 1. Here we have the total increment and first equilibrium iteration. Let's see how many we try. 4. So this is the first one. We have the residual force, very large, residual moment, very large. E4 and E5. Let's go to the next equilibrium iteration. The residual force looks like it didn't decrease, and residual moment, it decreased a little. E4 and E4. Let's go to the next one. E4 and E5, and then in the fourth one, E5 and E5. So you see that it's not decreasing. And then the software tries an equilibrium iteration, I guess. No. Yeah, so yeah. It doesn't try, actually. And then we have all this information here. We have this information here. Well, where we have the information about the cutback. The string has exceeded and blah, 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 many problems. And well, maybe it's not written here like we're going to do a cutback. We just have this information here. Increment 7 starts, attempt 2. So we are in the second attempt for this increment, and we're going to decrease these increments, and then in here it works. Okay, all right. Now we have spent 52 minutes, guys. Oh my god. All right, so we have finished analyzing the MSG file, STA file, and also the INP file. Let me think about what we're going to do here, because if I start post-processing these, I'm going to at least start this post-processing. To post-process the results, we are going to use a specific software, a post-processor software. And this is how it works in the industry. If you get to work in big companies, this is how it works. Actually, guys, since we have just a few minutes in this video, because I don't want it to be so much longer than 1 hour, instead of post-processing the results, I wanted to show how this module looks like in the Abaqus CAE application, which is the application that we have used in the previous exercises. So let me open up Abaqus CAE application. Here we have it opened, and now let's click on with the standard explicit module, and then to open that module in here, let me Control C the path to this folder where I have the .inp file, and then let me go to File and then import. Actually, let's go to set work directory and then paste that path here, and then click on OK, and then go to File, Import Module, and then you see that we are already in the working folder, and then set select .inp here, and then double click on this .inp file. And here we have the model that we have created. You see that the visualization here is very bad. I don't like it at all. And then in here we have the model definition. We can expand it, and well, you can study the definition of. I'm going to do an overview here, a quick overview, but you can study it in details if you'd like to. So here we have the part definition. With this part here, we can actually modify it. Here we have the definition of some sets. So we have these sets for the different PIDs that we have in the model. We have the definition of the materials. So for example, let me double click on this one. And then in this material, we have a density defined. Here we have elastic properties defined, Young's modulus and Poisson's ratio, isotropic material. And we have plastic properties defined, isotropic hardening, constant extrapolation, and we have the yield stress, zero plastic strain, and then anyways, we have that table defined here. And then we have all the other two materials defined. We have some sections here defined with the different properties. In the model, if we double click in one of it, you see that we have the thickness of this property defined here. The type of integration, in the thickness of the shell element, how many integration points. We didn't define this in ANSA, so these are the standard values that we have here. We can modify these parameters in ANSA, but we didn't do this. Well, anyways, let's go to the next item, profile. Well, we have a profile here because of the beam element. So double click here, and then we have the profile that was used for the beam element with radius equals 10. And then in the assembly, we have one instance that has everything. We have many sets here. We have two surfaces that has been created for the contact. These two surfaces that we have here. Connector assignments. We have something related to connector, translator connector. We have the section here of this translator, orientation of the first node. So we have the coordinate system here, and we have a rotation about the y-axis as we have done. Orientation of the second node is the same as the first node. Here we have the definition of engineering features. Let me see. Features, wire, this is for the connectors, coordinate system. Okay. Here we have the definition of iterations for the contact. Let me click here. Oh, actually it's here, iteration properties, double click here, and then you see that friction formulation is penalty. We have this friction defined here, isotropic, because it's equal in all sides. Let me see if there is anything additional that is important. Yeah, that's all we have for this. We have the friction defined. And then we have the definition of the steps here. So in the initial step, we have that boundary condition that we have defined, fixing the displacements here and here. Let me see, what is this? Oh, here we have the contact. Surface to surface, small sliding, tracking procedure, the slave and the master surface. Here we have the interaction selected. Yeah, I guess that's all that is important. So in the next step, we have the bolt pretension. We have the field output requests. Let's see how it looks like here. So double click here. And then you see that we have displacement, we have reaction force. let's see the history output. So we have this first one is for this set, measure rotation, and then here we are asking for rotations. This second one is for this node, we are asking for displacements and reaction force. Here we have the loads, connector load, and gravity. So, anyways, everything that we have defined in ANSA is defined in here. But it's not really so practical to create this model from scratch here in Abaqus application. Obviously that it is possible because this is not really so a complex model. This model is not so complex. You know, it's not that it's not complex. It is complex, but it's not so large. Because you know, when we work with larger models, the complexity is the same, but the model has too many entities, too many elements, and it's difficult to manage large models here in Abaqus CAE application. Okay, guys. So, here we have the connector section. Let me open it. We have it defined as a translator. We can modify it by clicking here. You see, we have it defined as a translator, and actually that's all. We have the constraints here. So here we have the couplings, right? Yep. That's all. 1 hour. Okay. So in the next video, we are going to post-process the results of this analysis. We are going to extract a curve like this and compare with this one. And anyways, and maybe we're going to already start the modeling of the bolts using solid elements. Okay, so I hope you liked it and see you in the next video.